Hello, young physicists. Welcome back to another physics tutorial. Today we're just going to be briefly going over a certain free fall problem that tends to come up in a lot of places. So I just want to take a look at that, and today's going to be a shorter video because it's just one problem. So today's problem says that a mortar launches a shell straight up in the air. 7 seconds after the shell is launched, it lands back on the ground. So how fast was the shell launched? Well, everyone knows the first step to solving a free fall problem or any physics problem is drawing a picture. So let's start there. Go ahead and pause the video here, draw your picture, and then once you're ready, go ahead and unpause the video and take a look at the picture I drew and see if it matches up, okay? All right, so hopefully you've drawn your picture. Now, what I intend to draw first is the mortar. If you don't know what a mortar is, it's a type of weapon that basically just launches shells like kind of in a rainbow arc, right? So it's perfect for projectile motion. So I'm going to draw my little mortar, and it's going to fire a shell straight into the air, right? So this shell travels up into the air, but it doesn't go up forever. Eventually, it must come back down, and so it eventually falls back down and to the ground, okay? So let's assume that the shell lands at the same height that it was launched at. That's a fair assumption in this problem, okay? The mortar can't be that big. So we know that our initial position is equal to our final position over the course of the whole path of the mortar shell, okay? Now we also know that the shell lands back on the ground 7 seconds later. So after a time of 7 seconds, the mortar shell lands. So it takes 7 seconds to complete this whole rainbow arc, up and back down, okay? So we want to know, how fast was the shell launched? Okay, well, we have our picture. Now the next step is to set up our givens and unknowns. So let's draw our table that we like to use for organizing our variables, right? So first we have displacement. You can use delta x or delta y. I'll use delta y since we're working vertical. We have initial velocity, we have final velocity, we have acceleration, and we have time. All right, so first, let's see if we can determine anything useful about this problem. There actually is a trick to this problem, and I want you to take a moment to pause the video and see if you can see the trick. It has to do with what we choose as our initial and final, okay? All right, so hopefully you noticed that the ball, or the mortar shell, sorry, spends half of its time on its way up and half of its time on its way down. All right, that's true for any projectile that is launched and lands at the same height where it's launched. All right, half of the path is going up and half of the path is going down. So, our best choice here in this type of problem specifically is to not make our initial, our launch, and our final, our mortar shell landing. We want to make either our initial point or our final point the top of the arc. Okay? We want to make either initial or final the top of the arc. And the reason for that, the reason we want to do it that way is because our velocity at the top of the arc is 0. Right? Whenever you have something being thrown straight up, it decelerates due to gravity, right? Its acceleration is downward, and so it's traveling up, but it's traveling up slower and slower until it reaches a certain height, and then it falls back down. For a moment at that certain height, it reaches a velocity of 0. So that velocity being 0 is really useful to us, and we want to make that either our initial or our final point. I think I'm going to go ahead and make that the final velocity up here so that our initial velocity can be our launch. Okay? Our initial velocity is right here. All right. Now, before we get ahead of ourselves, let's decide which direction we want to be positive or negative. It doesn't really matter. I'm going to go ahead and make up positive, but you're welcome to make down positive if you would like, okay? So we're going to say up is positive. All right, well, we know one of our pieces of information is that the final velocity is 0. The velocity at the top of the arc is 0, so our final velocity is 0, okay? We also know we're looking for our initial velocity. It's asking us how fast the shell was launched, so we want v initial. So we must have 2 more pieces of information here. One of them has to do with the fact that this is free fall. Our acceleration is going to be 9.8 meters per second squared down. So because it's down and up is positive, then down is negative, so our acceleration must be negative. So we have a negative 9.8 meters per second squared for our acceleration. Then finally, we have our time. Now, our temptation may be to say 7 seconds is our time, right? But remember, we're only talking about half of the path, right? Our initial versus final, or the interval over which we're interested in, is only half of the total arc. So if it takes 7 seconds to go up and land back down, then it's going to take half that time to go just up. So we're just going to take 7 divided by 2, and we're going to get 3.5 for our time, okay? So our time here is 3.5 seconds. This is the big key here, is knowing to cut our time in half, okay? We need to take half of our time. So if our mortar or our projectile had spent 10 seconds in the air, we would use 5 seconds as our time, okay? All right, now let's go ahead and solve the problem. So we are dealing with the last 4 variables here. We're dealing with our initial final velocities, our acceleration, and our time. So lucky us, we get to use equation number 2, which in my opinion is the nicest equation to use, okay? So we have this equation to work with, and we're just gonna go ahead and plug in our knowns and unknowns. So final velocity, that's 0. Initial velocity, that is VI. Acceleration is negative 9.8. And finally, our time is 3.5, okay? All right, so now, our next step is going to be to do a little bit of calculating. So 9.8 times 3.5 gives us 34.3. So 0 equals V initial minus 34.3. And if we add 34.3 to both sides, we get a final answer of our initial velocity, which is 34.3 meters per second, okay? That is the solution to our problem, 34.3 meters per second. And of course, it's going to be positive because our velocity is up initially. So that's the question. We found the speed at which our shell was launched, and we are done. So I hope you have a wonderful day, and take care.